start today's session, but maybe we wait for some 5 minutes so to see if anyone else is joining. Okay, I guess we'll get started, and if someone wants to see this, they can look at the recorded lectures later on. So today we have two demos. The first demo is about transfer learning, and the second demo is going to talk about automatic mix precision, or AMP for short. And we are going to see both of these things implemented with PyTorch, and this will be just kind of a motivation, or one of the applications rather, for both of these. And if you are working on a PyTorch code, how you can go about implementing it. So just a short demo for both of these. Okay, am I audible? Okay, so as I was saying, today we'll have two demos. One will talk about transfer learning, and the other will be about automatic mixed precision implementation. And both will show in PyTorch how we can go about doing it for a simple application, and you can look at that and modify the code accordingly for your own application. And for automatic mixed precision, we'll also see using the tensor board, the tensor core usage. Yeah. So maybe I'll talk a little bit about the demos before jumping into the main idea. So the transfer learning demo. So what we'll do here is, so we'll take a model which is called the VGGNet or VGG16. Okay, and this model has been trained on a data set. In fact, there used to be a competition called ImageNet Challenge, and every year of this competition, many researchers around the world, they used to present their models for the competition, and the entire challenge was actually the motivation behind the challenge was actually to improve the state of the art image detection algorithms, so image classification algorithms rather. So this ImageNet challenge, it had a data set called the ImageNet dataset, and this dataset basically it had many, some thousands of classes in fact, and so it was actually very difficult for the algorithms at that time to get a good accuracy on such a dataset which had so many classes. So one of the entries for this ImageNet challenge was the VGG16 algorithm model, and so this was trained on this ImageNet dataset which had I don't remember exactly, but more than thousands of classes. So what we will do today is, I don't know the exact number, but yeah. So basically the dataset had many different classes and the number was huge. So this VGGNet particularly, it had a bunch of as most convolution networks at that time had. So there is some architecture of this VGG16 model, and at the end there will be the final layer, which will be like a dense layer, or rather a classification network, we would say. So after going through the entire series of convolutions, at the end you have a sort of a classification network, I would say. Which is completely set set of dense layers, or you- the the kind of layers that you see in a typical neural network. Okay. So, and finally you have the number of classes, that many number of outputs as the output of the model. Okay. So this data set, what it did was, I mean, this model particularly, so through its training, in the in this part of the model, maybe let's say there is a class for cat in the original data set, and the model maybe have kind of learned certain features in this image. So let's say it learned to detect the an edge, let's say such as this, okay, which is coming over here, okay. Or then over successive layers it maybe learned something more complex like an ear shape, okay, and so on. So throughout the layers of this network, you ended up learning more and more complex patterns in an image, okay. And towards the end, whatever you have is just a set of feature maps, and which is eventually going to be a 1x1 cross set of feature maps. So it's ultimately going to end up being a 1x1 cross I would say k set of feature maps, and all of them are capturing something that is present in this image, okay. So the data set, the model in its learning training procedure, it learned to find the best type of features from any sort of images. So this data set had in fact lots and lots of images. So going over those several images, the model ultimately learned to capture the features from complex images, and if in fact boiled it down to a simpler one-dimensional vector, okay. So ultimately this vector is then passed through a set of neural networks layers, and ultimately down to your 1000 classes at the end, okay. So all of this is a typical neural network after this point, okay. And here there may be a softmax there, which is giving a probability for this 1000 classes for that image, okay. So far, any doubts? If you have any doubts, just maybe put them in the chat box. In the meantime, I will wait for some time. I hope I'm audible properly. A bit louder would be good. Okay, yeah, I'll try to speak a bit louder. So we have a question here. Can we use this transfer learning for binary classification problem? Of course, yes. I mean, the transfer learning part will come a bit later, but I'm right now trying to explain the original VGG VGG16 model architecture. Okay, so I hope the architecture's main idea is somewhat clear. So the point I want to convey here is that the original network, that VGG network that we are talking about, it was trained on many more images. So it was trained on a lot of images. That's all. So this original VGG16 model is trained on a complex data set and a lot of images. And this model has basically learned to in the first few set of layers, let's say till the convolution part is going on, it has kind of learned that how to capture the essential features from an image. Okay, so that is the part that this model has learned very well using this complex data set and a number of images it went through during its training process. Okay, so now and the model is also pretty long, like deep. Okay, so it has the number 16 is coming from it having a 16 layers. Okay, so and it has a huge number of parameters. So but the thing is, let's say you wanted to apply this same you basically wanted to piggyback on the thing that this model has already learned. So this model has learned really complex features. I have a question. So do we have CNN network and some classification network? Yes. So the first part of this is I'm just giving you can say a rough way of describing this network. So we'll see the actual model of this network in a little while, but on an intuitive level you can imagine that the network had a first part which is full of convolution layers and a second part which is full of dense layers or traditional neural network layers with some nonlinear activation functions. Okay, so the idea is that the CNN part, the convolution part of this network, it has learned a lot of complex features. Okay, and we want to maybe our classes are not these 1,000 classes. Maybe this 1,000 classes had some maybe general stuff like cat, dogs, humans, cars, or some data set. It had some classes, but let's say you wanted to train it for some totally different data set. Maybe you wanted to use this model for, let's say, some underwater image classification. So you could still do that. The reason you will be able to do that is because the starting few layers of this network has learned really complex features from images. And what we are going to do is instead of this bottom part, which is the classification network part, we are going to replace it, or maybe even a small portion of it is what we are going to replace, not the entire thing. Okay, so we would end up replacing this part, and instead we will have a part which will basically, let's say you have a data set which has only 10 classes. Okay, so this for your application, what you would do is you would keep almost the entirety of the VGG16 model, okay, along with its trained weights, but this last part, okay, this last part you will replace it and you will retrain it. Okay, this last part is what you will retrain, and what I mean by retrain is you'll train the weights only in this last section of the network, and let's say this will go on to your 10 classes that are actually present in your data set. So 10 classes of your data set. Okay, so that is the key idea. So you can replace, so when we are saying the term transfer learning, what we are essentially saying is that there is a model which has already learned some things, and it has learned by putting a lot of data behind it, and the amount of time required for training such a model is actually already huge, okay, and the amount of resources also. So, but we don't want to spend all of those resources again, okay, and we want to just modify the network slightly so that we can still use it for our own application. So that is the key idea. So without having to put the efforts to retrain the entire model, we are only going to retrain a part of the model, okay, and the rest of the model will hold its original weights.
I have a small question here.
Yeah, go ahead.
When I've trained the model, just imagine I have only 10 classes. When I want to retrain, should I actually maintain the same number of classes? Like,
Yeah, exactly. So as I am saying, the original VGG net had about 1,000 classes, but
okay,
for your model, let's say, it might be some other application, totally different application.
yeah,
Let's
yeah,
say it might even be detecting some anomaly in a medical diagnosis or medical
okay,
application. So in that set, you can still use the initial part of the model, which has learned
okay,
the feature extraction in these complex images,
yeah,
and you
yeah.
can completely replace this later part. In fact, even it need not even be a classification problem anymore. You can put a
Okay, I
GAN.
can just change the last part. The last,
Yeah, yeah.
yeah, okay, correct, correct. Thank you.
Yeah, so you can even replace it with a completely different type of network. You can even put a let's say an image generation, so a GAN kind of thing. You can even put that over it at the end, and uh, it will still do a good job of getting a desired result without having to retrain this big model that we are talking about, the VGG16 model. Okay.
Okay.
Yeah, I hope that answers the question.
Yes, yes, yes. Thanks.
Good. So besides that, that is what we will actually do today in the demo. So we will see that uh, the VG16 train model, we will use that, and we will replace the last part of it and train it on a different data set called the CIFAR data set, CIFAR 10 rather. And this data set has 10 classes, which are I mean kind of similar to the ImageNet dataset classes, but still you can the idea is that you can still this is just for a demo purpose, and you can do the same thing with some other application as well. But CIFAR 10 dataset is already available in the this PyTorch dataset, so that's why we have chosen. Okay. So that is the key idea of transfer learning, that you don't have to retrain the entire model for your new application. Instead, you can go about using a part of the model before, which is already trained, and for the rest of the part you can modify it and retrain it as per your needs. Okay. So that is the kind of motivation about the transfer learning that I wanted to convey. I hope this is clear. Okay. If you have any doubts, you can feel free to ask.
Yes, I mean this is something little bit different. I just want to know like one very basic question about deep learning. Like when the researchers are creating a network,
Mhm.
okay, how do they actually know that I need so many layers, that convolution, like how do they decide it? Like it's some kind of a hit and trial thing, or it's like mathematically they know that I need so many layers.
Yeah,
Like
actually,
how does it happen?
yeah, so in fact, for this specific question, you can actually go about digging into the ImageNet challenge, the way this challenge actually panned out throughout the history. So
Okay.
basically, over few years, I mean, it didn't happen immediately. In fact, the state of the art models on this ImageNet dataset right now, they
Yeah.
perform far better than humans, like, at classification tasks. So
Okay.
we have already surpassed the human accuracy it started from something which was far worse than human accuracy, and over the years, these models have completely uh, beaten us left and right. So the thing is, in fact, you can go into looking at some. I can point out few specific networks that you can look into,
Okay.
and each of these networks actually gave a gave a new idea or a new way of thinking about convolutions and the way we do classification. So
Okay.
first, maybe we can talk about the AlexNet. So this was probably the first time when people started to take neural, like deep learning and convolutions, a bit more seriously. So before that, people used to implement many standard methods to do classification problems,
Yeah.
and at this with AlexNet, it completely changed, and the game went in favor of using these complex deep learning models. So even for AlexNet, there were some what can I say, uh, some doubts that were raised at that point, that whether it had to be this big or so on. Like all of those questions were raised. Okay, but turns out that the next, I don't remember which was the immediate next model that
Mobile
came.
net, is it? Or
Uh,
mobile net came little later.
I don't remember exactly, but so the thing is, the models that came after AlexNet for few years, in fact, they were still models which were going more and more deeper, instead of getting any uh, good at representation at a particular layer. They were in fact trying to go more and more. They were just keeping on adding more and more layers, and uh, in fact more and more parameters, so to train. So that ended up happening. I think VG16 and this VGG18 and its variants, all of these were around that time only. And then some new techniques started coming up. So
Yeah.
ResNet and maybe InceptionNet,
Yeah. Inception.
these kind of models basically started introducing new ways of thinking about the process of convolution itself. So, as to answer your main question, like how researchers actually think about adding the layers and all. So,
Yeah.
they uh, the way we think about, like, let's say you want to train a model, so uh, that is not their main purpose as a researcher. So
Yeah.
when they are doing the training, they are actually looking at what is the representation capacity that my model has learned, and they
Yeah.
will not go just put some layers and get an output. In fact, they will try to analyze every single thing that they have done. So let's say they added a new
Every layer,
kernel.
after every layer, what has been extracted?
Yeah. So the kind of analysis that they will go through for making a model, so
Yeah.
that will be far different than the way we think. So
Okay.
the way we would apply for maybe an engineering application or so on, we would not probably go into analyzing each and every single layer. So,
Okay.
or
I
in fact,
I have
even
another question now. I mean,
Mhm.
just a continuation of it.
Okay.
So, like, I mean, I come from a hardware background guy. I mean, we make hardware for deep learning inferences, basically. Okay.
Mhm.
So, is it the model which is influencing the design of the hardware, or the hardware design which is influencing the model? Like, usually.
Mm, I didn't get the question
For
exactly.
example, we make specialized neural network accelerators. Okay.
Okay.
So based on, I mean, I'm more of a application user. So it's like I use different available models to see
Mhm.
how the inference and take place. I mean, the accuracy and the speed at which it takes place. Okay.
Mhm. Mhm.
So is it that uh, the the architecture of any neural network accelerator or the GPU, okay,
Mhm.
the model influences the architecture, or the architecture influences the model, like the capability.
In some sense, I mean, both are kind of influencing each other. So
Okay,
if you
okay,
look at architecture, so
yeah,
some architectures might be too heavy for a particular set of hardware. So
yeah,
if
yeah,
you want to, let's say, use a Raspberry Pi to uh, put a very big deep learning model, it might not
yeah.
be able to do you inferencing at a good speed.
Good speed,
That
yes.
might be possible. So then in case you might need for go for a like a NVIDIA Jetson or Ore,
Jetson, yeah.
those kind of, yeah. So the advanced architectures, they might help you in inferencing faster, for
Yeah.
certain set of architectures. Along with that, what might happen is so uh, the model might not necessarily uh, a particular architecture, if it's the hardware architecture, if it's very good, I mean, then it doesn't matter what model you are putting it through, the
Yeah.
hardware might do its job either way. But
Yeah.
in most cases, we sometimes might want to optimize this thing. You might want to uh, you don't want to put a very heavy board in the, let's say, so I particularly work in robotics. So uh, we we want to make an autonomous underwater vehicle, and
Yeah.
in this vehicle I can put a decent enough computation power, but I
Yeah.
don't want to overkill it. So I don't want it
Yeah.
to be so powerful that it will just generate a lot of heat and mess with other electronics or just consume a
Yeah.
lot of
Yeah.
power. So in such a case, the architecture or the hardware is kind of influencing what model I should choose.
Okay. Okay. Yeah. Yeah. It makes sense. It makes sense.
So in that sense, it depends from application to application, I would say.
Yeah. I think it's case by case.
Yeah, it's case by
It's
case.
just case by case. I mean, I think I mean, also it depends on the application, if it's commercial or defense
Yeah,
or medical and all those things. Like,
yeah,
I think,
completely.
yeah. I think we can just
Also,
go back to the previous thing. I mean, where you started. I think this will take a lot of time. These discussions.
yeah, it's okay. I mean, the
Yeah.
sessions are meant to be interactive, and in fact, I'm very happy that you are asking questions.
Yeah.
Okay, sure. So uh, that is the general idea of transfer learning that we will look at in today's session, and the next part or the next demo will basically uh, show you how this automatic mix precision uh, tool can be used in PyTorch, and as it was mentioned in 2 weeks back, I think, uh, during the PyTorch week. So that time the sir mentioned that how you can uh, basically see whether tensor cores are being used. So tensor cores are specialized parts of the hardware which are uh, enabling the automatic mix precision application. So uh, today in our demo we will see specifically that automatic mix precision will be used, and it will show that the tensor cores are being used for the same. Okay. So that is the overall summary of today's demos. Okay. If anyone has any questions, we can keep the tablet and tablet screen. We'll cover the questions and then we'll move on to the code. Okay, I guess so far no questions. So we will go to the codes and then maybe come back if the questions are required. So I shared a Collab notebook link. So I've shared a Collab notebook link, and you can just click on it and make a copy of it in your drive and get started with the demo. So also try to keep the, so I have actually connected to my local system, but you can change the runtime type to GPU and proceed with the demo. I hope the code is accessible to everyone. Okay, good. So the the first part of the code is just importing of several libraries. Maybe you can run this cell and run to ensure that it's working properly. Then here we are setting the device, so and just printing it. So if you have set the runtime type to GPU, you should be able to see device as CUDA. And yeah, so this is actually the specifications for our current application. So in this case, we are actually looking for training on the this CIFAR 10 dataset, which has only 10 classes. So classes of and we are just basically setting some learning parameters for our retraining purpose, and the batch size is also set. Okay, so then we are actually basically borrowing the VG16 model from torchvision.models. Okay, so this is coming with its default weights. So these default weights were trained on a completely different data set than the one we are going to use now, but we'll see how even those weights on first few layers can help us train for our application for this particular dataset much faster. Okay, so we are just borrowing this model, the model VGG. Okay, and we are printing the model. So you'll see that in this particular model, the first part of the model is features, which has been labeled as features. It's a set of convolution layers, and this is the typical convolution neural network architecture. So you have a 2D convolution layer followed by an activation, and then a 2D convolution activation, a set of max pooling layers, and this kind of thing will keep on repeating for some time. Convolution, convolution, max pooling, convolution, 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 max pooling, and this will keep on going. And over this part of the network, you have a huge number of parameters as well, and the network would have gone a considerable depth. So in this case, I think the number of convolution layers will be approx, I think, along with the convolution and the dense, the linear layers, it will be about 16 layers. Okay, so that is what the network is about. And you will notice here that at each layer you keep on increasing the number of kernels. So initially it was 64, then it's going to 128, 256 at this point, still 256, and then 512, 512, and at the end I think it's still 512. At the end you are having an output size of 7x7. So you started with an image which was I don't remember exactly, but whatever the size of the ImageNet dataset. So images in that dataset. So you started with a big enough size, maybe 228 cross 228, and you ended up going up to 7 cross 7. So which has in the length and width you have gotten far less height and width, and you have increased the number of feature maps to a good extent. Okay. And once you have done that, you end up flattening the entire thing, and at the end you are having this number of features of about 25088. Okay. And the output features, so you are basically putting a linear layer, which is like a traditional neural network layer. So the input neurons is this much, output neurons is this much, then followed by your activation, and you are also putting a set of dropout layers, okay, here and here, and basically for regularization purpose. And at the end you have these 1000 classes. So as I was saying, so the original dataset was trained on original model was actually trained from 1000 classes, and that is what the output of this layer is. Okay. So after this point, since this is the original model architecture and you have a set of train weights for this entire part, the first half, the convolution part, and you also have a set of weights for this dense layer parts. Okay. So what you do is you basically firstly to start with your training process, you have to kind of take the parameters of this VGG net, and you have to stop the training process for those. So you want to basically freeze the weights that you are having up till this point. Okay. So in this case we are freezing the entire network at currently. Okay. So you are freezing all the parameters of the network with this. Okay. So parameters dot requires grad is going to freeze the weights. Okay. And what you are doing is instead of this average pool, this layer, okay, you are putting an identity. So whatever is the size at this point of the from that you are getting from this layer, after that you are just putting an identity, and then you are going to put a linear layer, non-linear activation, and another linear layer, and down to your classes. Okay. So in this case our number of classes is just 10, right? So because of our new data set, it has only 10 classes, and you are replacing this classifier part of the network completely. Okay. I hope this part is making sense. So you have replaced the average pool and classifier part of this network. Okay. And then you have this setting the model to device, so that you can start with your training on GPU, and you are again looking at what is the model. So you will see that everything up till this point is exactly the same as the original VGG architecture, but this part is kind of different. So this part is having the input features as 5 and 2, followed by 10, 100 and 100 and 2 down to 10, which is the size of your datasets classes. And then you can run this cell to basically download your dataset. Okay. And it will take some time, so I will wait for some time, and till then if you have any doubts in the previous part of the code, you can go ahead. So till everyone downloads this dataset, we'll wait for a little while. let me know if the data set has been downloaded for them. Or is it still under process? Okay. Okay, so I hope the dataset is downloaded for everyone. So just to see what the dataset looks like. So this CFAR10 dataset, it is basically has a bunch of classes, and the images are kind of very small size images, about just 32 cross 32, and 3 channels RGB. And so we are plotting a 5 cross 5 grid of these images that are present in the dataset. So that's it. So the dataset looks something like this. Then we are setting our loss function and the optimizer along with the model parameters. So you will notice that for the rest of the part of the VGG network, which was borrowed, we still have requires grad parameter as false, but this newly added layers, so they won't have requires grad as false. In fact, for these newly added layers, the requires grad parameter will be true, and when you do pass in the model's VGG dot parameters, only those last few layers will have trainable parameters basically, and you are setting the learning rate, and this is the generic code for training a model. So you can run this thing and see it for yourself. This will train pretty fast. So unlike if you had to train the classic VGG model, which would be probably having a lot more number of parameters to train, and it will probably take a lot more longer as well. But here you are only training hardly from 512 cross 100 cross and then 10. So you are training a lot less number of parameters for the weights. Okay, so only the last part of the neural network is being trained, this much. Okay, so you can just train it and then run this final cell to check the accuracy of the model that you have trained. Okay, and you can probably go for a longer training time. if required. So the key idea is that you basically freeze the initial part of the model and keep the rest of it, or change it according to your needs, and retrain it. That's all. If anyone has any doubts with this, we can cover, or we'll move on to the next demo. I'll just wait for around 5 minutes if anyone is still running the code. Before I get to go to the next demo, would you guys like to give some feedback? Like, is this demo presentations helping, or should I go with some different approach? Okay. By the way, your mic is still on. So, yeah.
Oh, sorry.
Yeah. Trying to receive it. Good. Good. So the demos are fine, I guess. I mean, if anyone would like me to cover some basic the background behind these machine learning algorithms, that is also fine. I mean, if you can let me know now, I can basically revise my stuff and get back on it for the next lecture, so or the next session. So if there is anything in the session so far that you would like me to basically, so this course kind of expects some prerequisite knowledge on machine learning concepts. So if there is any topic that you would like me to cover, so that also I can cover, because the sessions go a bit short on time if you don't have anything to discuss for that specific week. So if you have any such topics, you can let me know. I can go ahead and uh, pull up my old stuff and cover that also in these sessions. Uh, you are feel free to list down any topics that you would like me to cover. Hi. Good evening. First year BTech student, can you give me some guidance regarding I mean, this might not be the best place to discuss that, but maybe I'll just send my email ID.
Okay. I think your screen is hung a bit in a sense, like there's infinite screens. Is it a problem from my side or your side?
The is the I'm moving my cursor. Is that visible?
Yeah, yeah, I think so because of that.
Yeah. Actually, I'm on the chat window.
Okay.
So Pushkar, in case you have any like, doubts apart from the topic of this course, maybe then you can shoot me an email. But as I was saying, it's like if you have any doubts from the content of this course, or so in the you must have seen in the demos of the course also, there is some prerequisite knowledge of machine learning that is expected, or and deep learning. So if you have any specific topics that you would like me to cover in the live session, so my primary focus will still be on the covering the that week's content. But if there is any extra time, I can pull out one of the topics that you are mentioning here, and I will also try to cover that along with the week's content, so as to cover that 2-hour requirement for these sessions. Okay, yeah. Feel free to put it in the chat box. Till then, we'll get started with the next demo then. So this connection is okay, good. So I will just share this link. Okay, so this is the link for the next demo. You can open it and as usual make a copy of this in your drive, save a copy to drive, and then you can get started with the demo. So in this demo we are actually looking at the automatic mix precision functionality that is available in PyTorch as well. So the requirement for AMP is actually a specific version of, I think, 1.6 and above version of PyTorch, and even certain architecture. So there's a requirement that the I think so before I don't remember exactly, but a certain architecture of CUDA, these GPUs, NVIDIA GPUs, the AMP functionality won't work on all those, but afterwards it works. I think Turing architectures it works for sure. So the Tesla T4 is having Turing architecture, so in your Colab notebooks it should definitely work. Okay, I'll just run all the cells at start itself. So in the meantime we can see the process happening. So this is the installation for tensor board, so you can visualize the utilization of the tensor cores. And so what we are doing here is we are just training a simple convolution neural network for the application of classification again, and the data set is again CFAR10. Okay, but what we are going to see here is the usage of the automatic mix precision. So as you must have seen in the lectures, so using AMP you can kind of fasten your training process in some sense, and also ensure that you have to work with less amount of data. So instead of going for the floating point 32 throughout the floating point 32 operations throughout the training process, in between layers you can keep them running with FP16, and essentially you have to crunch less numbers, and your training process might get faster. So that is the idea here. So we are just defining a simple convolution neural network here, and we have a ReLU activation on a convolution operation, then pooling, then again ReLU on convolution, pooling, ReLU again convolution. So about 3 convolution layers, and then we are flattening, and then your dense layer, and down to your fully connected layer, so where you are going to predict the classes. In general, you'll basically try to put a softmax layer here, so you can get out probabilities of each of the classes. And this part of the code is basically for the data loaders. You don't want to load the entirety of the data. So in the previous demo you kind of saw the size of the data actually. So it has huge number of images, so about somewhere in the order of some 170 million. Okay, so the data set is huge, but they are small images, but a lot of them. So but you don't want to load the entirety of it at once in your GPU. So we are putting some batch size and a data loader. Then basically we are creating our model, defining our loss function, optimizers, and this part of the code is actually the scaling. So you must have seen in the lectures videos, so what we'll do is at any particular uh, evaluation time or forward pass, we'll first store the weights in FP32 format, then we'll apply the scaling onto them, do our forward pass, train our models and get the new weights in FP16 only, and then scale them back down to get your FP32 approximations. Okay, I guess the code has, okay, the code is running, so we are just trying to reload this. Okay, well, this is not the important part. The important part is here. So till then that loads, we'll just complete this discussion. So the scalar is defined using this torch dot amp dot gradient scalars. Okay, and you're passing your model to GPU, and you're defining your tensor board writer, summary writer, and this is just a plot of the loss, training loss. But what you will see here is that not in the overview, in the GPU kernel, you'll notice that I showed a similar demo few weeks back for the PyTorch one, where we discussed, where we had a demo of denoising example from the convolutional autoencoder. That time you must have seen that the AMP was not used back then, so you were seeing that the tensor cores were completely unutilized. But in this example, we are seeing some utilization of tensor cores, and maybe you can increase that with a bigger batch size or so on. Maybe I'll try to, yeah. So you will notice what all operations are happening with FP16 here. So these are the set of operations that are taking place in the architecture which are on FP16, and they are the ones who are using tensor cores. Okay. So yeah. So I kept about 50 epochs running. Maybe for as a homework, you can try to see the comparison of this against without the use of automatic mix precision. So you basically have to comment out this line here, and you have to take this out of the loop here. Instead of going with this, you can just take it out of the loop and keep it running, and the scalar part you can basically comment out. Okay. So if you do that, you can get a and put a time around this, you can get a comparison of how the AMP is aiding in your training process, and so this will keep on running for some time. Probably it's overturning. The loss reduction much is not. Yeah, depends on the architecture as well. But this was just a demo to show the use of tensor cores for training with the AMP. I guess that covers the demo. If you have any doubts, maybe you can shoot. Any doubt? I hope the code is running for everyone. If the tensor board is not working, you just refresh the. Yeah. If you have any doubts, feel free to ask. Else, that is the demos that I had today. We can wrap up the session in that case. By show of hands, can you anyway, can you guys just let me know if everyone here is familiar with let's say a typical convolution neural network? If not, maybe I can cover that in maybe the next lecture or something. Or even if we have some time today, actually, if required. Am I audible? there are no doubts, then maybe we can conclude the session. If you have doubts, maybe I'll wait for about 5-10 minutes. Okay then. If no doubts, we'll just conclude the session. Thank you for attending. Okay. So there is. Okay. So we have about half an hour. I can give a rough overview of a convolution neural network that is implemented, let's say, in this example that we saw today. Just an overview. Yeah, sure. So maybe I'll switch back to the tablet. And you might need to be a bit more interactive in this process so that I can know if there is any doubt at any point. Okay. I hope my screen is visible. About 20% charge. Okay, so let's get started then. So before I jump into the actual scene in convolution neural networks, I would like to discuss the convolution operation. Okay. Without going too much into the mathematical definition of this operation, what I would like you to think about is just consider a 1D data set. Okay. Let's say this is some time axis, and you have a set of data points of some quantity that you are measuring. Okay. So on the y-axis you have some quantity x which you are measuring over time. And so this is like a time series data that you have, and you basically want to, let's say, approximate if you are familiar with the moving average operation. So what you would do in a moving average operation is that you want to somehow smoothen this data. Okay, so smoothen, that is probably a goal, I would say. Okay, so your goal is actually to somehow smoothen this data. What you would do is you take, let's say you want to go for a moving average, and you will fix a window. Okay, window, that is the first requirement. Let's say you had in this image that I'm showing, you have about 1 2 3 4 5 6 7 8 9 10 11. So you have about 11 points. So you had 11 data points. Okay, and maybe you decided that you want to smoothen this entire thing out. So a simplest way to go about doing is just take an average of this entire data points. Maybe that average might look something like let's say this. Okay, so that could be one way of smoothing this entire data out, right? So what you did here is you basically chose the window size as 11 because you set you chose all of your data points, the entire data points that are available right now. You chose all of them to smoothen it and get your one output. So you compress the information of 11 data points into a single data point, which is the average of this entire set. Okay. So once you have done that, let's say you might say this sort of an approximation is not a good approximation for the data set that you were working with. So is there a way I can delete this? So you might say that this is not a very good approximation of the data set because it completely lost all the variability in the data set. Right. So in that scenario, you might say, let's reduce the window size. Okay. So you might say, let me take three data points and look at their average and use that as a means to smoothen my data out. Okay, so we'll go with 3 now. So when you are going with 3, let's say you took the mean of this and this, and let's say that came out to be somewhere maybe around here. Okay, for some. So one way is that you just take the entire window of these 3, 1 2 3. Okay, take the mean of that and put the same mean for all 3 of them. Okay, that is one way. Then you would take the next set of 3 data points, which are this and this, and take a mean of all 3 of them. Maybe that would lie somewhere here, and then you can go about doing the same process, and in that scenario you would have some mean over here. Again for the next, maybe there is another data point, and eventually you got some mean value, let's say here. Okay, so now this is another way of approximating the data set, but this also has lost some of the information of the data set. You have approximated it better than the last time, which was just a constant number, and you kind of reduce this 11 down to 4 numbers, right? So the 4 mean values, you reduce the 11 down to 4, and this has captured the data set a bit better, right? So what you did here is you fixed the operation that you are doing over the window. Since I'm just talking the mean, so I would like to define the mean as some operation. Okay. So what operation is this mean taking process? It's basically you are multiplying each of these numbers. So each of these data points. I would go ahead and okay. So let's say these particular 3 data points. What you are essentially doing is when you are taking the mean, yeah. So you are taking the value of this x value, okay. You are multiplying it by 1, okay, adding all of them up. So I would like to say this is, let's say, value x1, this is x2, x3. You are taking this x1, x2, x3, each of them multiplied by 1, okay, and then you are dividing the entire thing by 3, okay, because you have the window size you have chosen is 3. For the purpose of convolutions, that the denominator that you are talking about, that is not something that we are going to bother much about, okay. So the size of the window does matter for smoothing, but what we are going to talk about here is basically these numbers. When you took the average of this, you basically decided that all of them have to be multiplied with just 1, okay. So if I draw this data set again, so what you did was you multiplied each of these values with 1. So what I'm going to do is let me draw another axis, which is I will call the kernel axis, and I'll come back to the reason why I'm calling this a kernel axis. On this axis you are having a new function. So the data that you initially had, that also you can imagine as a function, but on this kernel axis also you are putting one function. And in this case it's actually a constant function, okay. So this constant function is of value 1. So I've redrawn the dataset X, and I've also drawn a kernel function here. So in a way what you can do is you can imagine the process that you have done here, this average taking process. You can imagine it as a piecewise multiplication of these two numbers, okay. So the original data set is also one function which is going up and down, maybe like this, okay. And this window, this kernel window, is also something which is fixed in this scenario. So when you were calculating the mean of this part, you were having this kernel over here, and you multiplied, let's say, x1 with 1, x2 with 1 again, and x3 with 1 again, because this is a constant function down here. Then you shift this kernel window, okay. In the next step, when you are taking the mean of this 3 data points, the 3 data points over here, when you're taking the mean of these 3 data points, what you have done is you have essentially shifted your window from here to, let's say, here, because I'm taking the next 3 data points. And the thing is that this kernel function is going to be constant. Okay? This kernel function is not going to change, but it's going to move, or rather slide along this axis. Okay, is that making sense? Okay, good. So what you are doing again here is you are going to multiply this value with 1, this value with 1, and this value with 1. Okay, and then you are going to sum them up and divide it by 3. You get the mean. Okay, so what you are essentially doing, what I want to say is that two things you did here. You basically had a kernel function, okay, which is a sliding window basically throughout the length of this input signal that you had, and you are doing this operation of multiplying the kernel function piece element wise element with the inputs of the elements of your kernel. Kernel constant is going to vary for each window. I didn't get that question exactly. Kernel constant is going to vary for each window. I still didn't get the question. So do you mean to ask whether the kernel constant is still fixed? The kernel function that I am talking about is a constant function which has a value of 1 at all times, if that is what you are asking. Okay, so the kernel function itself is not going to change, but its location, the points which it is going to multiply with on the original function, that is going to change. So this function is basically going to slide over from in that direction and keep on multiplying with every set of 3 elements on the original function. Okay. Okay. So if you wanted to define what you did here, is that maybe I'll not go into the mathematical description of this function, but you can imagine this as applying a function, this kernel function k, on parts by parts of the original function. Okay, and not applying the function, rather applying the kernel function, taking its piecewise multiplication with the elements of the original function. That is what you did. Okay, and this by 3s maybe you can imagine that instead of 1 it was, let's say, 1 by 3. Okay, then this would mean that the constant values that you are multiplying each time is 1 by 3 with each of the values here. So if you had to go for, let's say, 4 window size, you would have divided this by 4, and this would all be that would added. You would probably add one more element here. Okay, and instead of 3 it would be 4. Is there any specific reason kernel function constant was chosen as 1? Yeah, good question. So in this example we are just choosing it to be 1. There is no restriction that this kernel function has to be 1. In fact, you can very well imagine this kernel function to be something like triangle. Maybe you can have it like this. So maybe this is 1 by 2, and I'm purposely choosing a very simple looking kernel function here. In reality, when you are implementing convolution neural networks, the kernel function is not even going to be 1D, it's going to be a 2-dimensional grid, and that is going to go over your entire image. Okay, but in this case I'm just imagining a simple kernel function. Okay, so what is going to happen here is, now you want to multiply. So what you have done here is actually you are saying that when I'm going to piece by piece take multiplication of my original function and this kernel. Okay, so the kernel is located only for 3 points. Okay, 1, 2, 3. Okay, so what you are saying is I'm going to weigh the middle point more than the first and last point. That is what this type of kernel means. Whereas in the first kernel that we saw, all 3 points were having equal weightage. So when as the kernel slides, it is giving equal weightage to all 3 points throughout the process. But if it was this kernel, new kernel that we are talking about, so I would say this is example 1, this is example 2. In this kernel, you are saying that the second point in the list always is going to be more important than the first and third point. And when this kernel shifts, let's say over here, it's again going to have the same shape, but again it's going to weigh the second point more than the first and third. Is that making sense? And that is just because of the shape of this kernel. Good. So you can make it far more complex. You can go for kernels later on which are not just 3 window size, they can be far more complex, and you can go for complex shapes like maybe a Gaussian curve, in which case you are looking for a center of the data that you are passing over, and you weigh that far more than the rest of the data around it. So the kernels can be anything, and there is no restriction on what this kernel function should actually be. But the reason for choosing different types of kernel functions is it will allow you to see what patterns are already present in this data set, right? Original data set. So for example, here specifically, when you took this kernel, let's say, which was a box kernel, I would say, the 3 data points are weighed equally, and you are just getting the mean of it. It tells you something that is together true for the 3 data points, but it doesn't tell you anything about the pattern of these 3. So here the 3 data points are forming a triangle like this, but here they are forming the opposite triangle. So this kind of phenomena will be captured if you had a kernel like this, which is varying from the 3 data points. So in the first case, when you took element wise multiplication, you will notice that the middle data point and the middle of your kernel, they were overlapping, and you will get a big product at this point, right? But in this case, when you apply this kernel over this part of the data, you will notice that this smaller number is multiplied with the bigger number, but the resultant product will be slightly less than what you would have observed here. So the variation in your original data set can be effectively captured if you have a kernel which is varying, or it shows a different variation of the instead of putting equal weightage over all the data points, it is having a varying dependence on the data point. Okay, so that is the whole idea of kernels. and the more varying kernels you have, the better your capture of the original data. Okay, any doubts at this point? Okay, so what we do next is, instead of applying this on a, how do we choose kernels? Yeah, so we'll come to that. So this kernels is actually set, so for a traditional neural network, the way the weights are a trainable parameter, in our case of a convolution, the kernels are going to be the elements of these kernels, they are going to be the trainable parameters. Okay, is that making sense? So the weights of the network in a traditional neural network, the way they are trainable, in this case, the elements of this kernel, so what shape it should have, all of that, basically these, the function itself, that is a training trainable parameter that you are going to have. I hope that answers the question. If not, you can ask. Okay, so maybe some more explanation is required for the trainable parameters part. Okay, so before I go to that, are you familiar with traditional deep learning architecture? So traditional neural network architecture. Okay, good. So in a traditional neural architecture, what you essentially do here is, I'm just going to draw one layer with 3 neurons, and this is one neuron in the next layer. So what you are going to have is this 1, 2, 3 neurons. I would call this A1, A2, A3 maybe, and there is a weight associated with each of these connections. Let's then call them W1, W2, W3. So what you are essentially going to do in this, to get the output of this neuron is, you're going to take W1 A1 plus W2 A2 plus W3 A3 and apply some nonlinear activation function, and along with your bias term maybe WB, I would say. Okay, so that is going to give you out the output of this neuron, and you have a good number of neurons in each layer of your network, and this ultimately is going to give you out one loss, and you're going to, when you're doing the back propagation, you are going to take the derivative of this loss with respect to each of these weight parameters and update them. That is the traditional neural network training procedure, right? In case of convolutional neural networks, the training procedure is related to, instead of training these weights, you are training for getting these kernels. Okay, so the kernels, since this kernel is going to be constant throughout the length of this network, or length of this data, you only need to learn these numbers. Let's say the first number, the second number, and the third number. Okay, so to learn these three numbers is your goal, and that is what through back propagation you are going to learn. I hope that clears it now. And I think that answers the second question that also we are having. How do we determine which kernel to choose for the CNN model? So the point is that we are not going to choose the actual value of the kernel. The model itself is going to learn it over the training process. Okay. So when it comes to now 1D data, this is how we imagine the kernel to be. But in case of a 2D data, let's say for an image, okay, so an image is basically a set of grid of numbers, right? So what you are going to do here is this entire image, let's say I call it some height and some width. Okay, so this is an entire image, but what I'm going to do is I'm going to choose a 2D kernel instead of a 1D kernel. So what a 2D kernel would look like is it's going to have, let's say, a 3x3 2D kernel is going to look like something like this. Okay, so there are some numbers on the blue numbers are going to denote the let's say the RGB values of your original image. Okay, I'm going to call them A1, A2, A3, A4, A5, A6, A7, A8 and A9. Okay, and the red values, or rather I will change the color, let's say green values, or maybe red is correct. So since I'm drawing the kernel in red, I'm going to, so the kernel is also now a 3x3 matrix. When going for a 2D data, the kernel itself is a 3x3 matrix, and this kernel matrix has also 9 numbers, which are K1, K2, K3, K4, K5, K6, K7, K8, K9. Okay, what you will do here is that the same procedure that you did in this case when you're applying the kernel to the data, 1D data, you are going to do the same kind of procedure here also for a 2D data. What you would do here is you will take, so the output is going to be A1 into K1 plus A2 into K2 plus A3 into K3 and so on till A9 into K9, and you are basically taking the sum of all of this, and on top of this you might apply some nonlinear activation. Okay, so this is the kind of function that you are going to apply over the entire data. So this kernel K1 that you are, so this kernel 3x3 kernel that you are seeing here, this kernel will pass over the entirety of your data set, and so there are different ways of passing it, but so it will keep on passing with shift of 1 every time. Okay, so right like this it will go over this way, then it will come down here, it will multiply over all the numbers of here, each of these, then it will shift, multiply with all the numbers here, again shift, multiply with all the numbers here. So that is what a convolution operation is essentially going to do in 2D. Okay, it's exactly the same what you saw in 1D, but it's just a matrix that is going to sit on another matrix and it's going to slide over it. Okay, that is what a convolution operation in 2D would look like. Okay, is that making sense? good. Okay, so once that is done, what you would do is, since instead of putting only a one kernel with these nine numbers, you might choose to do, let's say, you will choose 10 different kernels. Okay, so let's say I will, for the demo sake, I will just draw different types of kernels that could be present, and these are just some examples. They are not necessarily the kernels that you will definitely have, but I'm just drawing some demo. So let's say you have a kernel like this 111000000. So in this case, k1, k2, k3 are having value 111, and rest of them are having 0. You can imagine another kernel, let's say of this type, in which the diagonal elements k1, k5 and k9, they are 1, but the rest of them are 0. Okay, so this is another variant. So what I'm drawing is two different types of kernels that could be present. Okay, so these could be the kernels that your model ends up learning. Why did I specifically choose these examples? So the thing is, if your data, the underlying image, okay, if it had a pattern which is similar to this, so as I showed here, okay, so as we discussed, the kernel shape here is good at capturing that the presence of a kernel shape like similar to it in the original data set. Similarly, in case of a 2D kernel, a presence of this set of numbers, so 11100, all of them are the zeros, it will help you identify a horizontal edge in the image that you are working on, or it might, in this case, it might help you identify a diagonal or slanting edge in your image. So that is the kind of differentiation that different colors will allow you to. So similar to this, you can have 10 different shapes. Maybe you can have 111 along this diagonal, in which case you will have a diagonal or a slant line which is in this orientation you can identify. You can have maybe the middle line, but that will be more or less similar to this guy, so that won't work out. Maybe you can have a vertical line. Let's say you have a line like this. These are ones, rest are 0. Okay. So all possible scenarios that you can imagine on a 3x3 grid. Maybe you can even have a kernel like this, and all the others are 0. Right. So it's capturing a edge like or shape like this in your original image. So the whole idea is let the model learn all the different types of features in the original data set. Okay, on the original image. Okay, is that making sense? So that is the idea behind choosing different kernels. Okay, good. So the sorting this out. So what you do is, since there is a main difference between choosing convolutions for images and not choosing, let's say, traditional neural networks for images. So the thing is, in an image, these patterns are what are going to make more sense for you to identify, and it's not going to make much sense to, let's say, look at every single pixel value. Let's say you had an image in which there was a person. Okay. Now this person, he might be present in the center of the image, or let's say only at the corner of the image maybe. Okay. Even in either of the cases, the edges or the structures of the image, they are going to be same. that is not going to vary for person. That person is going to still look like a person even if he is half in the image or at the center of the image. So it's not a very sensible thing for us to directly take every single pixel value and pass it through or flatten it and make it a single column and pass it through a dense neural network architecture, right? So an architecture like this, it's not going to make sense to do that. Instead, you want to capture it down. You want to basically look at these patterns, make a simplified, much simpler representation of that information, and use that to, let's say, do your further tasks. It can be related to classification, it can be related to, let's say, segmentation or identification of the person in that image, and so on. Okay. You can even go and identify where exactly that person is located in the image. All of such applications are possible. Okay. So the point is that you are going for patterns rather than values. Okay. Is this part making sense? Good. So the goal of convolution neural networks is actually to search for patterns in images rather than looking at the exact pixel values. Okay. And so because in an image it might very well be that even though the person is exactly at the center of the image might be full of fog, and or it might be raining or anything, and the person is still there, right? So you want to still detect that person in that image, but the pixel values might be completely different than what you saw in the previous image. So it's the pattern that is more important than the values. Okay. So knowing that, as I just said here, you have a lot of information, but when you go down to a pattern, that information can be shrink down. It need not be so you don't need to retain all the information of every single pixel value here. Instead, you can retain information in a smaller vector, which is telling you what all patterns are present in my data. So when I'm saying this pattern, it's a much simplified way of explaining a convolution neural network. That is not necessarily exactly what a convolution CNN model is doing, but it serves the purpose. Okay. So when you are storing patterns, you might need to store very few of them. You might need to store a less amount of information. Let's say I'm looking at pattern 1. So pattern 1 is present in this image, pattern 2 is maybe not present in this image, pattern 3 is present, pattern 4 is not present, pattern 5 is not present, maybe pattern 10 is present, or something like this. So the numbers that you will ultimately boil this image down to, that is going to be a far low dimensional representation of the original image. Okay. So that is the key idea. So typically, I will just briefly tell what a typical convolution neural network architecture looks like, which is very similar to what we saw in today's example. So let's say you had an image of size 32 cross 32, okay, from this CIFAR 10 dataset, and you had a kernel. Maybe you had 10 such kernels, each of size 3 cross 3, okay, which ran over the entire image, found 10 different patterns. Okay. Now, what you essentially try to do is, once you have identified or found these patterns, what comes out from this 32 cross 32 image, it might look very different from the original image actually. So it might just show that at this part of the image, a pattern, let's say, such as maybe this edge. So it might show that a pattern like this is located at this part of the image. That is all that the information after passing over a convolution layer is going to have. So passing over a convolution layer on the original image might later end you up in a new image, I would say, which is basically encoding the information that this kind of edge is present at this part of the image. Okay, so I'm having low charge, but I don't have the charger here. But I will quickly try to wrap this up. Okay, it's not even charging. Fine. Okay, so I'll just quickly tell. So once you have done one convolution operation, you get something called the feature map. A feature map essentially means what feature is present at what part of the original image. That's all. Okay. Once you have done that, you typically pass it through a max pooling layer. So very simply, if I want to describe a pooling layer, is that it is basically aggregating the information together. So a max pooling layer is basically going to tell you it can reduce the size of the entire image by, let's say, half. You are going to take maximum value in all of these 3 by cross 3 set of images, 3 cross 3 pixel values, and again you are going to take maximum, so on, and it can a 2 cross 2 max pooling kernel, or for example, it might go over and reduce the size of the image by half. Okay, so that is what we essentially try to do in a convolution neural network. You first apply a kernel, get out a feature map, okay, and then try to reduce the size of this feature map by applying a max pooling layer kind of layer. Okay, so I'll just note down convolution and max pooling. Okay, and this operation you keep on doing for a set of n number of times. Okay, let's say you did it for 3 times, as we saw in today's example. Ultimately, after reducing every time the image size by half, the 32 might become 16, then it might become 8. When it becomes that 8, you would have had a lot more feature maps than you had before, because every time you are, let's say, adding these kernels, 10 different kernels, 10 different feature maps you are keeping on adding to the image. Your original image is now changed from 8 cross the 32 cross 32, in fact cross 3, because it is an RGB image. It might change to an 8 cross 8 cross, let's say n, which is the number of feature maps you have at that point. Okay, so you might have that. What you would do at this point is you will flatten this. Okay, flatten it and get a single vector as like this, and then you take the flatten this single vector and you put a neural network, basically traditional neural network with a bunch of layers, and your final layer will have, let's say, 10 nodes to classify the entire image into 10 different classes. Okay, that is what a typical convolution neural network architecture looks like. So I think I'll stop at this point. If you have any doubts, you can ask. I went over the last part a bit in a rushed manner because the charge is also low and the time is also up, but I hope that gives you some understanding of what a convolution network is like. Okay, good. So maybe I'll stop the session officially now at this point. Okay. So yeah, thank you for attending. And maybe if you have any such doubts, you maybe even ask so that I can go over it a bit ahead of time. So I will better prepare the content for such explanations rather than the way I explained today. So it was ad hoc. Instead of that, maybe if you have any more suggestions of such topics, maybe you can let me know for the next session. Okay. Then we'll wrap up the session for now. Okay.